Welcome to our biosphere. It is heavily impacted by the atmosphere, surface, and the sun. To understand CO2, we need to see CO2. To do that, we need to become quite small. Let's shrink ourselves 100 million times. You okay? We are looking at a cube of space measuring 40 angstroms across. A stack of 1,000 would be nearly as tall as dust. But we still can't see CO2. That's because molecules at normal air temperature are zipping around faster than the speed of sound. And since we'll be dealing with photons, let's slow down time by 200 quintillion times. Ready? Now we can see. Meet your new friends, nitrogen and oxygen. A word of caution about your new friends. Oh my gosh, don't let them drive. They will crash into each other and exchange energy or give up energy 5 billion times each second. And no worries, your friend CO2 left to go shopping for photons. We'll find her later. This is what happens to solar radiation when greenhouse gases aren't around. Nitrogen and oxygen were relatively unaffected by the long-wave emission. Let's go find some CO2. I looked at 40 cubes, nothing. Where is she? But I did find this, H2O, moisture. Let's fire a photon. This time, the long-wave emission was captured by moisture. We felt this before when weather gets hot and muggy. H2O is a broadband greenhouse gas. It absorbs more than 3 times the bandwidth of UV emissions from the ground. It is also about 10 times more abundant than CO2, making it more than 30 times more effective at insulating the atmosphere. But let's keep looking for CO2. It took a while, 700 cubes later, but there she is. Let's fire a photon. What happened? CO2 is a narrow-band greenhouse gas. It absorbs only a few emission frequencies. That photon was at the wrong frequency. But don't worry, H2O will capture it. Let's fire another photon. Ah, another wrong frequency. Let's fast forward to an emitted photon with the right frequency. This time, the long-wave emission was captured by CO2. The photon frequency was within the narrow band that CO2 can capture. Let's explain this using an accurate parallel. Insulation from your attic helps insulate from heat loss, just as CO2 insulates the atmosphere from heat loss. Let's bring the insulation down so we can see its cross-section. The pink insulation represents the insulation from atmospheric moisture. The black line represents the added effective insulation from CO2. Now let's double CO2. Doubling CO2 only increased your insulation by 3%. CO2 is 1/3 as effective and 10 times less common than H2O. So it is no surprise that empirical evidence shows that H2O's greenhouse property plays in the major leagues, while CO2's greenhouse property plays in the minor leagues. On the bright side, CO2 plugs a hole in the frequencies that H2O captures, and empirical evidence shows CO2.greenhouse has a significant initial response. What do you mean by initial response? CO2.net equals CO2.greenhouse plus CO2.green, which have opposite forcings. We studied photon interactions with CO2.greenhouse. Now let's look at its alter ego, CO2.green. CO2.green includes the interaction of CO2 with flora. CO2 makes flora healthy. CO2 makes flora grow. While current CO2 levels are okay for C4 type flora, C3 type flora are suffocating. The parallel for C3 flora living on 420 ppm of CO2 is like expecting humans to live on oxygen levels found at the top of Mount Everest. C3 type flora grow about 58% more with each doubling of CO2, and the majority of all flora is type C3. C3 flora includes all trees, most grains, and most cool season grasses. So changes in atmospheric CO2 has a huge impact on the growth of flora. Let's fire another photon. What happened? CO2 green was absorbed by the leaf. The leaf unfurled a bit. The photon never hit the ground. The leaf, being farther from a black body than the soil, does not emit as much long-wave radiation. Black bodies are excellent long-wave emitters. A green leaf isn't a good emitter. Soil is. A leaf or flower unfurling would be a fast biologic response, maybe minutes to hours. A slower biologic response, maybe a month, might be cool season grasses growing more in response to higher CO2.green. Note how little light there is that reaches the ground. Would you rather be out in the open or under the tree? You've walked through a forest on a hot day. You know it's cooler. As a child, you've madly run on tiptoes over hot sand at the beach. You know that the grassy spot is cooler. That coolness comes from a combination of shade, evapotranspiration, and the higher heat capacity of water in plants. Industrial CO2.green is also associated with aerosols. Aerosols reflect radiation back to space and help form clouds that mostly cool. We know that CO2 has many climate change properties. We also know that the empirical evidence from the study says that CO2.net has dampened global warming. But that evidence only gives totals for CO2.net, not for each property. Fortunately, there are ways to discern individual properties, but that is for later studies. And of course, CO2.green can be further broken out by its aerosol and flora properties. And flora properties can also be further broken out.